Hey there, everyone. You may or may not know that in addition to working here at Library of Congress, I've also been a grad student for a couple of years studying data science at the George Washington University. Um, and I wanted to show you all before GW cuts off my access to their cloud computing service. I want to show you all something that I made as part of my, I guess, my thesis or my final capstone project. It's called FolkRAG. It is a retrieval augmented generation system for cultural heritage materials, and it uses materials specifically from us here at the American Folklife Center. So there's going to be some, we're going to go over some stuff here that everyone, I think, already knows, but I think it's still helpful for setting the scene. So archival data. When you have an archival collection, we all know it typically exists in multiple forms, or is represented in multiple ways. There's a catalog record that provides basic bibliographic information. There's a finding aid that gives detailed context and arrangement information. And there are also potentially digital objects online in lock.gov from that collection. Each of these have their own metadata schemas, their own descriptive methodologies or what have you. And a real challenge that we are dealing with every day is that these are sometimes connected, but not always, and not usually in a sort of sensible way. So yeah, a catalog record might not link to the finding aid. Digital objects might not link back to their source collection, and so on and so forth. And researchers, and indeed us, we have to search in multiple different places just to piece everything together. And that fragmentation makes research unnecessarily complicated and really time consuming. So currently, to successfully navigate these collections, you really need significant expertise in archival research, which is something we all have, but we can't just trust other researchers have that. And on top of that, they can't just simply come in and ask sort of like natural questions along the lines of like, what did the, I saw an interview one time, I don't remember all the details, but I want to know, like, what did that Vietnamese interviewee say about the ingredients in pho? You can't answer that. You can't ask that question. You have to dig for hours. And to do so, you've got to understand controlled vocabularies, archival hierarchies, and complex search strategies. And even experienced researchers often need help from other librarians who know these collections intimately. This has definitely been my experience working the reference desk. And if you're trying to find something specific across multiple collections, that could take hours or even days of searching through different systems. So here's a diagram of kind of to represent all these different blobs of data that sometimes talk to each other, sometimes link to each other, sometimes don't, and it's quite a complex web. So if anyone is watching this that is not affiliated with or familiar with AFC, well, I'm going to give some background because all the materials I worked with for this project come from it. So AFC, established by Congress in 1976 through the Folklife Preservation Act. Our mission is to preserve and present American folklife in all its diversity. We house the Archive of Folk Culture, which dates back to 1928, when it began as the Archive of American Folk Song. And our collections are really rich and varied. We've got like everything from folk recordings, music recordings, and oral histories to ethnographic field notes and photographs. And our materials document cultural traditions and living cultural heritage across America and the world. So the diversity and complexity of our collections that I love, with their mix of formats, languages, and time periods, made them an ideal test case for this project. We are like the only division in the library with this sort of multi-format collection. We collect everything. And because we collect everything, our materials present some pretty interesting technical challenges, So for this project, we had to process handwritten correspondence, transcribe audio and video recordings, handle multiple languages and dialects. And I'm an archivist by training and by trade. I work here, and I love this work, but this project was honestly born out of my frustration with, born out of the richness of our resources versus how frustrating it is to work with our discovery systems. So it's just a little bit of background of the data we're working with and why I started this in the first place. So what is FolkRAG? It's a tool that I, along with a fellow student, Jonathan Shield, developed to address these challenges. So at its core, FolkRAG is a retrieval augmented generation system. It combines large language models, or LLMs, with sophisticated information retrieval techniques. But what makes it special compared to other tools of this nature is how it's tailored specifically for archival materials. A short version is that when a user asks a question in plain language about AFC's materials, FolkRAG then searches across all of the available descriptions of our collections that it has. So catalog records, finding aids, digital object metadata, while maintaining the crucial context and relationship between these materials. And most importantly, when it gives you an answer, unlike something like ChatGPT or Claude, it always tells you exactly where the information came from and shows you where the information came from, maintaining the sort of academic rigor and attention to provenance that archival research requires. And importantly, it has a retrieval accuracy of 94%, which is high. But we'll dig into exactly what that means as we go on. So what is a RAG? What is RAG? So we're going to go over some key concepts here. So RAG, or retrieval augmented generation, combines three main elements. The first being retrieval, which is finding relevant documents from a database. Second, augmented, or augmentation. We are using those documents to enhance our system's knowledge. And then third, generation, which is creating a natural language response to a question. So think of it like a reference librarian or an archivist who first would find some relevant books, who would then read them, and then explain that information to you. And to make this work, we needed three components. One, a vector database that stores documents in a way that captures their meaning. Two, an embedding model that converts text into numbers that represent that meaning. And then a large language model that can generate human-like responses based on the retrieved information. So let me break down some technical terms you're going to hear. You've already heard some of these, but you'll hear them throughout the presentation. So first, embeddings. These are ways of converting text into numbers that capture meaning. For example, in our number representation, the word, for example, violin will be closer to fiddle than to boat because they mean similar things. So, yeah, embeddings capture semantic meaning. A vector store, number 2, is like a special catalog that uses these number representations to find similar documents. So instead of just matching exact words, it can also find related concepts. And third, chunking. Chunking is our term for breaking large documents into smaller pieces. So think of it like having both a full book and its chapter summaries. Sometimes those smaller pieces make it easier to find exactly what you're looking for. And I should note that getting the right chunk size is crucial. Too small and you lose context, and too large and you might miss specific details because you just have too much information. So, data acquisition and processing. To build FolkRAG, we developed a comprehensive web scraping pipeline to gather 3 types of data. First, we scraped all the EAD XML finding aids available for every AFC collection. In parallel, we pulled their corresponding MARC XML records, and then we used the lock.gov API to get the JSON metadata for all of our digital objects in P1, particularly focusing on, well, once we had that metadata, we focused very specifically on file locations and types. So that metadata let us structure wget requests to download the actual content files. There were a lot of them, as you can see. So once we had audio files, audio and video files for things like, oral histories, folk recordings, what have you, we used OpenAI's Whisper large model to transcribe them, which gave us nearly 11,000 machine-generated transcripts. I don't have examples of these transcripts as part of this presentation, but trust me, they are remarkably accurate. I was stunned. So we also ran about 4,300 PDFs through Tesseract OCR to extract their text. And then we also acquired almost 30,000 existing transcripts and text files created by the library, all through lock.gov. But the real challenge, it was honestly pretty easy to do all that first stuff, but the real challenge came in metadata processing. We had to build a system that could extract and normalize identifiers from URLs in various formats, generate matching patterns for different resource types, and preserve the information between all of those components. So, for instance, when processing EAD and MARC records, we had to carefully map hierarchical elements like title, date, subject heading, while maintaining their context and source attribution. And our final metadata schema includes everything from basic identification fields to specialized archival elements. And it's all stored as structured JSON to maintain compatibility with our vector store, which is a system called Deep Lake. But we didn't start with Deep Lake. We started with something called FAISS, or Facebook Artificial Intelligence Similarity Search, which is generally the go-to for vector stores. It has really good GPU support. It processes really quickly. But we hit a wall with handling metadata. Using FAISS required cramming all the metadata into a single field, which made it almost impossible to filter efficiently or maintain those important archival relationships. So that led us down the road to using Deep Lake, which stores each metadata as its own, what is known as a tensor. And this was crucial because it let us preserve the full archival context for every single document chunk that we had. So each document chunk inherits all the metadata from its parent document, collection info, dates, creator names, everything. So this means that a small chunk about, for example, a fiddle player carries the full context of the collection it came from, who recorded it, when, and where. And this proved essential for maintaining archival integrity while enabling granular search. So, technical overview. We're gonna, it's gonna be a little dense, but hang on. So we store all of our documents in something called Deep Lake, which lets us perform efficient similarity searches. We chose something called Instructor XL for our embedding model after extensive testing showed it had superior understanding of archival language compared to other models. We also implemented what is called hypothetical document embedding, or HYDE, where we generate potential answers to help improve our search accuracy. And finally, we use TF-IDF re-ranking to ensure that the most relevant documents rise to the top. And we did all of this, started with a small sample data set of a single collection. I believe it was the Perl R9 collection. And we gradually scaled it up to the full corpus of all of AFC's materials. So, our RAG architectures. In what was called our naive RAG architecture, or our basic first attempt at this, if you look at this diagram, I'm going to talk you through it. So the user query is processed and embedded using the same model that generated the vector store. Cosine similarity is then used to measure the semantic similarity between the query and the stored vectors. The top K documents, or just like the top number of documents that are found, that's a parameter you can set. It can be 1, it can be 5, it can be 50, it can be anything you want. It's just the number of documents you want your system to return to process the answer. Those top K documents are selected based on this similarity. They're forwarded to the LLM, which then generates a response. Once the relevant documents are retrieved, the system combines their content into a unified context. A structured prompt is crafted for the LLM, which includes the query, the metadata, and the explicit instructions on the desired response. And for efficiency, only the metadata from the highest scoring document is used, basically to avoid unnecessary processing and to ensure that the response is relevant to the user's query. So this architecture provides a streamlined and effective way of delivering contextually rich answers to user queries, which is great. And here is an example of the query as it is passed to the LLM. You can see we're actually giving the system instructions, like only use information. Like basically this is telling it to don't make anything up. I'm not going to go over it in detail, but I found crafting this quite amusing. Yeah, you're basically telling your LLM not to hallucinate. So now on to more advanced architectures that we tried. The first advanced RAG system adds a novel step before document retrieval. I already referred to this as HYDE, so yeah, I'll talk more about that. So it uses hypothetical document embedding, which we call HYDE, and this is how it works. So the LLM first receives an input query and then generates a hypothetical response to it. It then combines both the original query and the hypothetical response into a single hypothetical document. This document is then embedded and sent through the standard retrieval and response generation process. And then to ensure the output's factual integrity and reduce hallucinated content, the system controls what is called the temperature, setting it to 0.7 during generation of the hypothetical response. When I talk about setting temperature, a lower temperature is the way that we get the LLM to not go too nuts with, or not get too creative with its response. And surprisingly, this advanced architecture dramatically improves the reliability of the document retrieval and the response generation. So yeah, let's talk a little bit more about this hypothetical document embedding. So you can think of this as something like an archivist's or librarian's sense of intuition. If you ask about, I've already mentioned this before, but if you ask about pho ingredients, a good librarian might think, I'm probably looking for a document that mentions noodles, beef, and broth. So we just do the same thing computationally. We generate a possible answer and then search for documents that match both the question and the hypothetical answer. And this just helps us find more relevant matches than just searching with the question by itself. And here is an example of how we kind of prompted the LLM to do that. Rewrite this query to be slightly different but similar in meaning. And you're a document that answers this question. Funny, right? So some evaluation. So we tested different system configurations using vector stores with chunk sizes of 250, 500, 1,000, and 2,000 characters, and 3 different models. Both naive and Hyde architectures were evaluated with about 100 questions, measuring accuracy based on top K retrieval. So the naive RAG showed pretty poor performance, as you can see. You might want to zoom in on this. Hyde improved accuracy by about 10 to 20% across configurations. 250 character chunks performed similarly, but slightly better to 1,000 character chunks. And the best performance came from Hyde with Instructor XL embedding models, or Titan. So these results informed how we would approach testing on our full data set. We dropped using a model called Mini LM from our future analysis because the results were frankly awful. And then we proceeded with only the 250 and 1,000 chunk-sized vector databases, containing something like 1.6 million chunked documents. Well, 1.6 million for the 250 chunked data, and about 400,000 for the 1,000 chunked documents. And then we enhanced further. We enhanced our Hyde system. So let's talk about Hyder. So Hyder is where we enhance our Hyde generator to generate 2 additional hypothetical documents for a total of 3. Each pseudo query is generated by progressively higher temperatures, so 0.7, 0.8, 0.9, to ensure some variety in the generated responses. The generated content undergoes cleaning to ensure quality. In cases where the model fails to generate an adequate output, valid content from other hypothetical documents is taken. So each of the 3 hypothetical documents then undergoes separate retrieval. We then increase the overall fetch documents from top K to top K times 3. Therefore, we, let's see. So yeah, then we deduplicate those documents that are returned. We incorporated a re-ranker to help us bring the total number of documents retrieved back down to the original top K value that we set. So the re-ranking uses a weighted sum calculation to measure relevance. It reorders the documents and then drops those that exceed the top K value. Those that are left are then sent onwards to the LLM to generate a response. Very exciting, right? I'm going to explain what some of this means now. So TF-IDF, term frequency inverse document frequency. Imagine you're looking at a cookbook. Common words like, say, the and appear everywhere, so they're not super helpful for finding specific recipes. But words like pho or folk life, I guess, are more rare and therefore more meaningful. TF-IDF is a mathematical way to capture this idea. It gives higher importance to words that are frequent in a specific document, but rare across all documents. So HIDER, or advanced version of HIDE. So like I said, instead of one hypothetical answer, we generate several variations of both the question and possible answers. It's kind of like asking several librarians at the same time who might think about the question in slightly different ways. Then we use that sophisticated ranking system that we went over that considers three things, just to reiterate. It considers how well the words match using TF-IDF, how recent the document is, so newer documents might be more relevant, and how many of our search terms appear in the document. And this combination helps us find the most relevant documents more consistently. After using the enhanced HIDE method with 3 hypothetical documents to beef up search and retrieval, we found that it dramatically outperformed our previous configurations. You can see in this graph here, if you trace the green line, it shows that our accuracy, our answer and retrieval accuracy when using HIDE boosted all the way up to, like 93, 94%, compared to where we started with that blue line with our naive RAG, which it barely cracked 70%. And we found that the best configuration for the system, and potentially for, dare I say, all cultural heritage materials in a RAG system like this, we found that at least for the systems that we tested and the configurations that we tested, a smaller chunking strategy was more beneficial. We settled at 250 using this HIDER architecture. That's the word. Was hugely beneficial, as was using the embedding model in Structure XL. So what does this mean? I know we've gone over a lot of technical details, but what does it mean? So number one, we achieved 94% retrieval accuracy, which is a huge deal. And more importantly, we connected systems that have been just siloed for, frankly, decades. But there's still more to explore that we didn't really have time for. So, first up, I really wanted to integrate images, not just as attachments, but integrate them into the database in a way that understands their context and their relationship to texts and metadata. So, imagine searching a term and finding not just mentions in documents, but related photographs with an understanding of how they connect to each other. Second, we wanted to move beyond a system that handles single isolated questions to a more kind of conversational interface, being able to, instead of asking isolated queries, maybe a researcher could explore with follow-up questions, and the system would maintain that context and build more understanding over time. That would just more closely mirror how actual archival research happens. But, there's only so many hours in the day, and we didn't get to that. But maybe some other time. So yeah, thank you so much. Thanks for listening to me talk for a long time. You can download FolkRAG and try it out at this link, github.com/darkivist/FolkRAG. And now we're going to get into a quick demo. So now that we've gone through all the slides, this is FolkRAG. This is what we made. Really simple, really clean user interface. A couple of different tabs. First being the query interface, where we can ask our data questions, our data and metadata, questions. And then second tab is our vector store creator. This is where, mostly for, reproducibility, where we can make new databases, new vector stores from whatever data we happen to have. There's a little directory tree guide here about like how your data is supposed to look and be structured before you go ahead and build that database. There's some guidance here, all text files, all documents have to be encoded as UTF-8. All files, because this whole project is tailored to the way AFC does things, all files have to have a recognizable AFC naming convention. Same with transcripts. And for our metadata, the metadata has to be structured exactly in the same way that we pulled it via the lock.gov API. And there is also there's code in the Git repo to make sure that you can do that should you so desire. So I can go ahead and demo this since I have some demo data here, just to show it in action. If we were running this on the entire corpus of AFC's material, like is represented in these 3 entries over here, it would take about 12 hours to build. This should take more like 2 minutes. Fingers crossed. So we select our data directory, which is actually wrong now that I see it. Data, demo, or demo data. I think that's right. We'll select our chunk size. We determined that for cultural heritage materials, the chunk size best suited to that, to preserving the data and the context, is 250. So that's each chunk is 250 characters. We'll select our best model in Structure XL to generate embeddings, and we will go ahead and click create. Cross our fingers and yep, it's working. A little icon up here says this is running, and it says processing metadata. So we are just going to wait and see what happens. Okay, it's finished processing the metadata. Now it is splitting everything into 250 chunks and attaching the metadata, well, splitting it into chunks and generating embeddings, and attaching metadata to every single chunk. So that means that when we go to generate answers in the other tab, when a chunk is retrieved, like when a little bit of a document is returned as being a match, the metadata is also returned for that, not just for that chunk, but for the document that it came from. So we have this sample doc metadata displayed here just to make sure that everything worked correctly when we generated the database, which is really good because you don't want to waste, like I said, 12 hours building this thing and then discover, oh, none of the metadata was found or attached. So you can see here, basic identification. So the title of this document was Man on the Street. Creation date is 1941 in Dallas, Texas. Contributors are our old buddy John Lomax, Jerry Stillwell, Dan Ruggles. Online formats are text and image. Subjects are personal opinion, interviews, personal narratives, so on and so forth. notes are included here. Part of a series of interviews made by John Lomax in Dallas, Texas in 1941. And then importantly, there's a link to the item on lock.gov. I mean, this is just from the metadata. We can click and see if it's actually correct, which it is. There it is, Man on the Street, Dallas, Texas, December 9th, 1941. And there we go. Next item. Brandy McDougall reads and discusses This Island on Which I Love You from 2020. We've got the contributors here. This is a sound recording, American poetry. And the notes tell us that this is from Living Nations, Living Words. And once again, we can go ahead and check that that is correct, which it is. Living Nations, Living Words. This Island on Which I Love You. And just for the sake of killing time, we'll look at the third document here. Freed Waters. Again, from 2020. Poetry and literature. I think this is also Living Nations, Living Words, right? American poetry, color, Indian authors, some recordings, and yeah, Living Nations, Living Words. And once again, there is the link just to check that that is correct, which it is. And you'll see here, total documents with metadata found in this test set were 169. So that's pretty good. I think this data set is something like, I don't know, 180 documents or something. It's, I think it's like 1% of the entire corpus. So yeah, we'll just wait for this, twiddle our thumbs. For a minute. Vector store created successfully. Great, we've made a database. We've made a vector store. But I guess it's time for the main event. Let's query our data. We could select any one of these and it would basically do the same thing. The only difference is these top three are all of AFC's material in P1, and these are our sample sets down here. When we query the entire corpus, it does work. It just takes something like 3 to 4 minutes to return an answer. And I respect everyone's time more than that. I also respect my own time more than that. So we're going to query the sample 250 chunk size set. And a question that I've gotten very used to asking this data, mainly because I know that this document is part of the set and the metadata is included. So I know that if I answer it and it doesn't generate a response or doesn't return the metadata or something goes wrong, like I just know that this is supposed to work. So let's give it a try. So question is complete this sentence. And who among us has not received a reference question that was like weird and esoteric? You know, there's the old cliche of someone coming in and saying like, hey, I'm interested in this book that has a green cover and a monkey riding a bicycle on it. Maybe, but maybe it wasn't a monkey, maybe it's a giraffe. Our traditional discovery systems aren't really equipped to kind of deal with that. This probably wouldn't answer the question I just spewed out, but it can answer questions like this. And other questions. I mean, I know that we are about to have our holiday party, and a challenge that people have is to cook something that is based on a recipe from the collections. this would be a fantastic way to do something like that. But for now, I'm going to ask, complete the sentence. The mules are not hungry, they're lively, and what? I don't remember what the mules are. They're hungry and shrug. So let's see what FolkRAG thinks. Documents found. It's getting an answer for us. Okay. The sentence is completed as the mules are not hungry, they're lively and gay. This information can be found in the context provided, specifically in the file sr22a.txt. The full line from the context states the mules are not hungry, they're lively and gay. This lyric is part of a song recorded on November 3rd, 1937 in Akron, Ohio. The song is titled The Old Skipper and was performed by Pearl R&I. It was recorded as part of a field recording session conducted by Alan Lomax and Elizabeth Lomax, who are listed as contributors in the metadata along with Pearl Nye. So yeah, half remembered details resulting in a pretty full answer. The first sentence of the response is just the text from the document reproduced as is, and the rest is the text combined with the metadata by our LLM, which is Claude, Amazon Claude, in order to provide a coherent, sensible, and fact-checked, and importantly, cited response. So yeah, this is what we built. I hope you like it. If you have any questions, please email me. And thanks so much.